Well, what's up, everybody? Hey, hey, hey. It is 2 minutes after 2 hours UTC. I am terribly, unusually late. So, yeah, just last minute things pop up, and it's like, uh-oh, I need to take care of that. But what saves me every single day is the I've got an alarm set on my smartphone. So that's set for 1:45 UTC. Set for 1:45 UTC. So gives me 15 minutes to finish whatever I'm doing and get all set up to go. And it's not a huge setup, but it all does take a little bit of time, right? The process is the uh, the alarm goes off. I finish what I'm doing. That usually takes 1 or 2 minutes or so. Just close whatever I'm doing. If I'm watching some kind of a video, it gets stopped. You know, all of that takes a couple of minutes or so. Then I get up and I go locate and then transfer laptop, this laptop. Um, for some reason, my Mozilla Firefox just crashed. So I'm going to restore this tab, the uh, the chat. Now I need to go over. I need to go over here and make sure that I'm not gonna freeze up my poor Linux machine. So locating the laptop and um, getting it in here takes another few minutes because I usually know where it is. So it's just a matter of, going there, unplugging it, and then bringing it back in here. So let's see. Creator Studio. Hola. Hola Arinstro. Hola. So messed up HOS presentation we'll redo after the show. Possibly. Uh, Most of the time after this live stream, I've got an adrenaline rush because of this, but I crash and burn pretty quickly, pretty quickly. So yeah, usually within half an hour or so, I'm like, I think I need to go take care of these strange weak feelings. So so feel free to send me an invite, um, Bobby. But uh, yeah, I'd say at this point there's a uh, probably a 30-70 chance, 30% chance at this point, maybe a 25% chance. So, because yeah, I'm just feeling feeling just lazy and tired and slothy. So it's it's great. So cheers. This is the hydrogen hydroxide. This will keep me, you know, a little on the chill side. I'll get my uh, I'll get my smartphone going on video, my video going on my smartphone. Should be coming up here. Methinks. Yeah, there I am. Quite a lag. Quite a lag. It looks like about maybe 30 seconds or so. So yeah. Sorry. Being out here in the middle of nowhere, we are actually at one of the ends of the line in terms of power and internet and phone. We have DSL. So uh, and yeah, so our internet comes in via DSL, and as I said, at least where we are here, we're sort of at the end of the line. We're the last pole. So yeah, we sort of well, for what we're paying for, it is good enough. I'm really glad that we can do this. I was a little worried about that it wasn't going to be quite good enough, but it looks like it is. So I'm really glad about that because then you know we can all be here talking astronomical things. So yeah, I hope everybody's doing well. It's just coming down to sunset where I'm located over here in southeastern Arizona, United States. It's local time is always 7 hours behind UTC, so it's 2:09 UTC. I've got to subtract 7 from that, and that makes it 1909. And 1909, you can also call that 7:09 p.m. So where I'm located, it is very conveniently 7:09 p.m., about to be 7:10. So it's 7:09 p.m. on 7/9. So peace to that and cheers. We should have caught it when it was 7 hours 9 minutes 18 seconds. That would have been pretty cool. This is a long minute. There it goes. Okay, now it's 7:10 p.m. So that was very cool that we caught 7/9 on 7/9. Must must mean it's going to be a good show, right? Oh, Arnstro. Wow. Let's see. Let me uh let me see if I can figure out where you are. 6:39 a.m. So you've got to be so you're uh wait, 6:39 a.m. here? No, it can't possibly be 6:39 a.m. where you are. It it's got to be. Oh, okay. I am with you. I'm with you. Okay. Yeah, I don't think it can be 6:39 though. It's got to be an 11. Um, but some some countries have half time zones, don't they? So 39, would that make sense? No, it'd be like 41. Oh, I don't know. So you're UTC plus 4.5. Okay. All right. So you're are you uh Russia? I mean Eastern Europe, right? Eastern Europe? Not like not like uh not like not the Netherlands or anything. You're east of that, right? You're east of that. Um Chat lag. Um Thanks, Bobby. Yeah, so you got to be like Eastern Europe, yeah, or uh, maybe West Central Africa. Cool, cool. Okay. Well, that's all that needs to be known. That's one of the cool things is that we are not, physically meeting up here, but we are virtually. So we are in the same space. It's just a different kind of space. Cool. Central Asia. Uncle Bill keeping track of the time while he keeps track of 53 other live streams, keeping them clear of trolls and posting links in all of them simultaneously. This is an amazing, just totally amazing. Thank you, Uncle Bill. Uncle Bill, how can we get more of the Weekly Space Hangout crew to hang out here? How can we do that? I I I refuse to be um, annoying, right, or rude. So they've been extremely nice. They've been extremely nice to put my live stream up on their calendar. So every day everybody sees that. So maybe not everybody sees it. I'm not exactly sure. I'm just trying to strategize here a little bit with you folks, uh, um, and and uh, and I would definitely like your feedback, right? Because I mean, especially now. Now, look, there is room for a lot, uh, and there is definitely room for those um, that are doing it now to just expand in huge ways, and that's and uh, but you know Weekly Space Hangout is now on hiatus for a couple of months, and I'm just wondering what those people uh, uh, will do. Or, I mean, do they take a break from everything? Um, Not exactly sure. So um, yeah, I forgot that there were some half shifts in the world. So yeah, uh, I think that's amazing. So Afghanistan, wow. Okay, yeah, that's very cool. Uh, pretty amazing that that the reach is that far and in such an amazing place. Well, I hope that you are there having an amazing time, just like us all, right? I mean, I'm here having a totally amazing time. So, you know, wherever you may be in the world, I do hope that you're having a really amazing time. And that's one of the things that I really like about astronomical things is that looking at things astronomically sort of makes everything really amazing, really incredible. Yeah, nice. Worldtimezone.com. Uncle Bill and his weapons, his ninja weapons. he is showing us his ninja weapons. That's great. That's great. Yeah, it's we're here in southeastern Arizona. We go through a monsoon season that usually starts in early July and goes through September, sometimes into October, and the monsoon is just beginning to rev up now. But even where I'm located, I'm located at a pretty high elevation. We're at about 4,500 feet uh, above uh, above the ocean level. Yeah. Um, cool. Yeah. Interestingly enough, our desert flowers pop out in March and April. We have a winter here, which can actually get pretty cold. It can get pretty cold. It can get below 0 Celsius here. Um, so yeah, it can get pretty cold. Um, but um, but we will get um, some precipitation during the winter months, especially like January, February. We'll get some nice uh, storms. They slam into the West Coast, right? They decimate California, and California, like absorbs all that energy, and it's all we get is this nice rain. So, these things, these winter storms, can be pretty strong. And yeah, they just slam into the West Coast. Bam, but by the time they get here, they're just nice rainy days, and they can rain for a couple days, you know. Um, hey there, Gilles. I am doing great. I hope all of us are doing well. Um, yeah, you can tell the seasons by whether there are mudslides or wildfires. Yeah, yeah, that's the truth. That's the truth. All right, well, cool. Well, I hope everybody's doing well out there. I saw that Tony Darnell with Deep Astronomy. I think if you go to deepastronomy.space, check him out. He's also on YouTube as Deep Astronomy. He does a couple times a week. He does a live stream. It's sort of like an interview um, type of thing. Um, and then he also puts out these separate videos. And I noticed that he posted a new one sometime today, maybe this afternoon. I forget exactly when. Uh, um, uh, um, uh, I was just reading Bobby's message to Jill. I think that's great. Yeah, I I really like Rabbit. Also, I think it's really interesting, and it's an interesting concept. Um, and but it's sort of it's like on that thin edge of it's like, well, is this really legal, or are there some copyright problems? Because I mean what what I could do, right? For instance, if I wanted if I wanted you to come watch this with me, see what that says? Theoretically, I could rip this video, um, uh, rip the video, upload it to this YouTube channel, and we could watch it, right? Theoretically. So yeah, I I think it's balancing it's balancing there. I'm not quite sure. I'm not quite sure. So all right, well, cool, Uncle Bill. Yeah, yeah. It is pretty casual. It is, and I think I really like it that way because it's to me. I mean, when I uh, when I talk astronomy amongst friends, this same for sure. Um, among face-to-face friends. Okay, this is exactly what I would be uh, um, uh, this is how I probably would be talking, and I would be talking about these particular subjects that I have been now uh, for quite a little while, a few months or so. Um, but yeah, I and the I'm gonna have to think about video production quality because yeah, this is pretty this is pretty uh, I don't know, low level, um, pretty amateurish in terms of that. Um, I do, I think it can work. I think it can work, but I am definitely open to suggestions and stuff. I just, I mean, I want this to be um, different than what is out there now. Just a different angle on the same kinds of things, right? But just a different angle. And yeah, it's it's a vacuum that needed to be filled. Yeah, yeah, and as I said, one of my big things with pretty much everything I do is that one of the things that really motivates me is that I want to get better. I want everything to get better and better and better. Um, I actually think that my presentation has gotten a little bit better. There are definitely fewer ums and ahs than there was at the beginning. Probably, I'm just getting used to it, right? It's becoming a habit. Be at least being aware of the urge to say and ah. So it's has anybody ever heard of Toastmasters? The Toastmasters organization. Raw. This is raw astronomy. That's that's actually not uh, a bad phrase. Raw astronomy. Hmm. All right. All right, Uncle Bill, do you see what you did? Yeah, as I said, I'm going to stick with what I'm doing. The only thing that I can be is me. Can't really be anything else. It's too hard. So as I said, the only thing that really isn't me about this is that I definitely do not talk this much. I just I just don't. I just don't. Now I'm thinking these thoughts. So basically what I'm doing here, right, is I'm just thinking out loud. So, these are the kinds of thoughts that I would have. Um, and I'm just vocalizing them so you know you can, excuse me, so you can hear them. Uh, Last time I heard about anyone doing stuff with them was in high school, but yes. Okay. Let's see. So I where should we go tonight? Or today, however you want to put it. Posted a couple of papers over on my Discord server. Let's take a look at those. The second one I posted was particularly interesting because I thought that they gave a very wonderful description of white dwarf stars and their characteristics. I thought they did just a fabulous, fabulous job at uh, wordsmithing uh, a very understandable and very reasonable um, description of white dwarfs and their various characteristics. So let's take a look at that. Um, so I am over here at archive.org, and this came out just today. Just today. Um, just saw it, pop up in the last hour, right? Hour and a half, something like that. And I've got the chat up. Okay, cool. Um, um, so these guys took the Gaia Data Release 2 catalog and this online tool called the Virtual Observatory and created a catalog of white dwarf uh, stars candidates. Right? Here they call it a white dwarf catalog, but it's really a catalog of white dwarf candidates. So, things have to be confirmed, right? You can't. That's one of the processes of science is replication, being able to um, uh, replicate someone else's experiment, um, or try to solve the same problem in a different way and come to the same answer, right? If you can come to the same answer, then it gives you a lot of confidence, right? That uh, that uh, what you're thinking is probably true. Anyway, so they went through Gaia and picked out 73,221 white dwarf stars, or at least stars that have some resemblance to a white dwarf star, have the characteristics uh, that define what a white dwarf star is. So, and I really didn't post this for the actual content here, um, which you can read. It's a long paper. Okay, look. So it's 17 pages long. 17 pages there. So, yeah, it's a long paper, right? But this introduction is absolutely fabulous. Whoop. This this introduction tells you pretty much everything that you really need to know about a white dwarf. So then, you know, they get um, into how they collected the data, how they analyzed the data, uh, you know, um, any kind of conclusions, discussion, you know, any of that, and then it's done. But this first part, this introduction, is great. The white dwarfs are the evolutionary endpoint of low and intermediate mass stars, namely those with masses at the main sequence of less than 10 plus or minus 2 solar masses. So thus, white dwarfs are one of the most common stellar objects. Their structure is relatively simple. Now that to me is a red flag statement. So their structure is relatively simple, and their evolutionary properties are reasonably well understood. Yeah, that's another red flag. And reference therein for a okay. So white dwarfs contain a core of degenerate matter. So degenerate matter is a state of matter. Imagine um, uh, imagine a sort of a regular um, material. Doesn't really matter what it is. Okay, it can be anything, right? Uh, uh, you know, um, yeah. I mean, it can be anything. Um, so imagine like a lump of glass, right? Okay, so those atoms and molecules are arranged in a certain way, and um, interestingly, interestingly, there are gaps in between the atoms, right? There are gaps in between the molecules, right? Little tiny gaps, but there's a lot of them, right? So the first stage of degenerate matter is what's called electron degeneracy. And electron degeneracy is when all those atoms have been squeezed together tightly enough so they're all touching now, right? Um, but the electron shell has enough outward pressure to hold it stable. So that's called electron degeneracy. And that's why, and that's how you can pack half a solar mass into an object about the size of the Earth because of electron degeneracy. That's how much space is actually in between things, especially in a star. So the next phase of degeneracy. Oh, I should mention that white dwarf stars are stars that are electron degenerate. So that's where they stop in terms of a collapse. All right. A drink of hydrogen hydroxide. Cheers. So white dwarfs contain a core of degenerate matter, electron degenerate matter. Massive white dwarfs, those with a mass greater than about 1.04 solar masses, have an oxygen and neon core. Um, the core, the core of those less massive than about 0.45 solar masses is made up of helium, and those with masses in between, which are most of them, have a carbon and oxygen core. So imagine that. When I realized what that meant, it was a great, uh, and interesting sensation, and that is, imagine um, uh, an object the size of the Earth, right? Half the mass of the sun, um, completely and totally made of carbon atoms, as close packed as they could get, right? Well, what is that? That's like that's sort of like a diamond. So yeah, these are like Earth-sized diamonds. It's very cool. If that's actually what's happening, right? It's really, yeah, it's really hard to be sure. It's really, really hard to be sure what's going on. Um, we do not know what's going on under the atmospheres of these white dwarf stars. We really don't know. We think that, you know, high mass white dwarfs have oxygen and neon in their core, some kind of uh, solid state, right? And then uh, some of them, the least massive ones, have helium in their core, but mostly all the other ones have carbon and oxygen. It's just very, very cool. So, given that the lifetimes of the progenitor stars of helium core white dwarfs exceed the Hubble time, the observed helium core white dwarf population is expected to be the product of binary star evolution, where episodes of mass transfer occurred. That just that that would just speed up the the star's evolution. The more mass, the more things sort of go. So if a star can build up its mass, the faster it'll evolve, become a white dwarf sooner than when it may have. So the bulk of the mass of a white dwarf is concentrated in the degenerate core, acting as an energy reservoir. Regardless of their core composition, white dwarfs are surrounded by an extremely thin atmospheric layer. The, the envelope, which approximately represents only 0.01% uh, of the total mass of the star, is is the responsible for the energy outflow. So that thin envelope of material is responsible for all the light that we see. Um, this envelope is basically formed by a helium thin layer with a mass ranging from 10 to the minus fourth solar masses to 10 to the minus 2 solar masses. So, just not a lot of stuff. Um, Large envelope masses trigger helium ignition at the base of the shell. The helium layer is, in these cases, surrounded by an even thinner layer of hydrogen with masses in the range of 10 to the minus 15th to 10 to the minus 4th solar masses. For approximately 20% of white dwarfs, this hydrogen envelope is lost. From a phenomenological point of view, white dwarfs that exhibit hydrogen lines in their spectra are named dA, while the absence of this feature is generally referred to as non-dA. In particular, those which only present helium features are known as dB white dwarfs. Yeah, like a diamond in the sky, except way more dense. So white dwarfs are degenerate and long-living objects. Thermonuclear reactions have ceased, and their evolution is a long gravothermal cooling process. They're just cooling down. Apparently, that's all they're doing, right? They have no new internal energy source. They're just really, really hot, and they are radiating slowly, you know, slowly enough that it takes like 10 billion years to cool down. So consequently, the white dwarf population retains important information of the history of the galaxy. Much of this information can be recovered by analyzing the white dwarf luminosity function, which is defined as the number of white dwarfs per bolorimetric magnitude unit in cubic parsec. Mwahaha. Let's see, blah, 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 blah. The white dwarf luminosity function has been used to study in the study of both the thick and thin disks, and more recently, the bulge. White dwarf's mass function. There's a clear concentration of white dwarfs at about 0.6 solar masses, as well as the existence of a low mass peak at zero point 0.4 solar masses. As mentioned before, the existence of such low mass helium core white dwarfs is mainly due to mass transfer interactions in binaries. So there you go, Arnstro. Let's see. Moreover, additional observational studies suggest the existence of an excess of massive white dwarfs near one solar mass of unclear origin. So they can be used to study and characterize different kinds of clusters. Additionally, the white dwarf population has been used as an astrophysical laboratory to test non-standard physical theories, such as the variability of the gravitational constant or the existence of exotic particles. So that's kind of interesting that I I guess I didn't know that people were studying the variability of big G. That sentence is like an oxymoron, right? The variability of a constant. It constantly varies. No, it varies constantly. I don't know. What does that mean? So yeah, I just think that describes white dwarfs really, really well. Our current understanding of what they are, and what they're up against, and you know uh, what we think is happening, right? And there's well, what they say they've identified 73,221 of them. So holy moly, yeah. I did a survey of white dwarf stars back in the early 90s, and over the course of like 2 years, I I measured, I did photometric measurements of something like, I want to say 83 white dwarf stars. I mean, it was slow going. It really was, because the conditions had to be really, really good. And but just checking up on the chat here. Basically, they're using gravity to verify. Yeah, yeah. I mean, you never really know. I mean, lots of things can be misinterpreted. They are one thing, but we don't know about that one thing. So we think it's something else, and it seems to match all of our models and everything else, right? And it's like, well, yeah, we need to be able to see that somehow. Um, yeah, I don't know. At least be able to measure it. Not exactly sure how to go about doing that. All right, well, cool. I think I'm sort of looking at the clock, and it's like, oh, it's a little early. It's a little early, but if I get going on something now, it's gonna probably be it's probably gonna be uh it's definitely gonna go over, right? It's definitely gonna go over an hour. So it's like, hmm. And it's kind of interesting that there was a paper on white dwarfs. How just yesterday we were talking about uh, what's that African tribe, the Bonobo. I don't remember now. Anyway, they have some kind of knowledge of the white dwarf that's orbiting Sirius. So yeah, they every single time that the white dwarf is directly between Sirius and us, they have this big this big thing, and it happens like every 60 years, which happens to be the um, um, orbital period of Sirius B. So yeah, who knows? Who knows? All right. Yeah, I think I'm going to get out of here. I think I am. I'm going to get out of here a little bit early. No worries. No worries. White dwarfs are awesome. They're the end states of stars. They're they're at least one of three different types. Uh, how we think sort of stars end up, and um, maybe three or four different types. But you know, as I said, we really don't. I don't think that we really know yet. Um, there's a lot of white dwarfs, and I'm not seeing a lot of planetary nebulae, for instance. I mean, the story goes that um, uh, that when the white dwarf forms, it sort of, blows off the outer atmospheres of the star to create uh, some kind of fluorescing, reflecting gas cloud that can form a ring or some kind of interesting shape. And I guess I guess maybe we don't see them around most white dwarfs because of the time scales. Maybe it just takes a couple 100,000 years for those clouds of material to just sort of stop glowing and are far enough away that they don't really reflect anything anymore. So that material is out there. It's just not being illuminated anymore. Uh, but yeah, it's those kinds of things where I mean, we see that there are white dwarfs um, in the centers of most planetary nebulae. So yeah, I don't know. One of those mysteries. All right, I think I'm going to get out of here for now. Join Bobby over on his Rabbit to listen to some music from the Hearts of Space. As I said, I may or may not. I'm going to get a little bit more dinner here, and then, as I said, I'll probably crash. So who knows though? Send me an invite, and if I get on, I get on. If I don't, I'll catch you next time. No worries. All right, I'm going to get out of here for now. Take care, everybody. Hit the thumbs up. Hey, I got a thumbs down the other day. I got a thumbs down. It's like somebody's paying attention. All right. Take care, everybody. Yeah, the link to Bobby's Rabbit stream is over on my Discord server. So go take a listen. You can't really go wrong. Can't really go wrong with Hearts of Space. So, all right. Take care. Enjoy. I'll see you on the spin. Bye.